Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good day I bid to all my panels out there. My name is Muhammad Afiffuddin Suhaimi, and today I'll be presenting my undergraduate project entitled Development of Simplified Structural Strength Assessment for Small Vessel. My undergraduate project is being supervised by Tuan Haji Yahya Samian.
Alright, this is the contents for my presentation. By the way, if my explanation is too quick or too fast, you may pause at any point of the video. Thank you. Structural strength of a vessel is very important to be assessed in order to ensure the survivability of the vessel at various types of loading. This assessment is crucial as it enables the vessel to operate safely. In addition, all big ships or merchant ships such as dry bulk carriers, container carriers, tankers, tugs, and passenger ships are mandatory to be designed according to rules and requirements of classification society. In current practice of traditional boat building, engineering calculations are being omitted and the boat will be built according to the rule of thumbs. The traditional method does not have any approval nor guidance from any naval architects, and it offers builder to design any vessel freely. Common technique applied by the traditional boat builders is boat frames only will be made after the hull has been constructed and completed. Clearly, that the traditional technique may bring failure to the boat's structural strength. In other words, traditional boat building technique is like a trial and error design process. Hence, the idea of this research is to propose a simplified method of structural strength assessment for small vessel. The simplified method then could be used to assist the local boat builders and boat designers. Based on the previous problem statement, the research objectives are to develop a simple method of assessing structural strength for small vessels and to verify the effectiveness of the developed method. The main scopes of this research as shown on the screen, while the flowchart shows the overall scopes of the research. The strength assessment is important as been mentioned before, and this assessment is a compulsory routine in ship design, especially for large size vessels such as merchant ships. Common theory being used in longitudinal strength assessment is Macaulay's theory, which it helps us to analyze the total bending moment and the midship section modulus for a ship or a vessel. In total bending moment analysis, strength curves are very common and each strength curve is strongly related. First is the wake curve. It shows the longitudinal distribution of the wake in the ship. Second is the buoyancy curve. It presents the longitudinal distribution of the buoyancy. Third is the load curve. It shows difference between the wake and the buoyancy ordinate of each section throughout the ship's length. And the last one is the shear force and bending moment diagram, where this diagram presents the highest bending moment occurs at particular ordinate of ship section. After that, to determine the midship section modulus, one must refer to the midship scanting list or midship scanting table. Then, geometrical and flexural properties for each scantling are calculated in order to determine the midship section modulus. We shall now proceed to the simplified strength assessment for total bending moment. Murray's method has been chosen and adopted in this research for the total bending moment simplified strength assessment. It is similar to the conventional method as this method also used to determine the total bending moment. Murray proposed this method as an approximation method because average wake distribution aft and forward amidships is used to determine the static water bending moment, while fixed equation has been developed by Murray in order to determine wave bending moment. Next, we move to the simplified strength assessment for midship section modulus. Currently, there is no simplified method for section modulus analysis. However, a research has been done to find hydrofoil section modulus using simplified method recently. The simplified method has been developed using correction factor concept. The correction factor is derived from calculated bending inertia of the hydrofoil. It is to be presumed that same concept can be applied to the midship section modulus. Right now on your screen is the overview on how the correction factor works. The shown flowchart is a quick overview on this research methodology. For your information, two models were used in this research. First is Model A. Model A is from an existing hull. The particulars as shown on the screen. For your information, Model A is a patrol boat owned by Department of Fisheries Malaysia and having a 300 horsepower outboard engine. Rhinoceros 5 has been utilized to assist the 3D surface modeling of this model. Next is Model B. Model B is a passenger boat owned by Kejora, and this boat is operating at Tanjung Surat, Johor, which is located in Pengerang district. This boat is having two units of 150 horsepower outboard engine. In this section, we will be discussing about both conventional and simplified methods used in the research. First is the total bending moment analysis by using MaxSurf stability module. These are the steps used in order to obtain total bending moment using MaxSurf stability. Why MaxSurf? It is because this module is using Macaulay's theory in its computation. In other words, MaxSurf stability will be representing Macaulay's method, which is the conventional method to analyze the total bending moment of a ship. Next is the analysis of total bending moment using Marais method. Table shown on the screen is the detailed steps on how to use Marais method in the total bending moment analysis. We shall move to the midship section modulus analysis. In the simplified method of section modulus analysis, three categories of sectional shape are considered: triangular section, typical midship section, which is planing hull, in which typically small vessel uses this type of hull, and box-shaped section. To understand better the concept of correction factor, we shall apply the concept to the triangular and box section. Shown equation is the general equation used. Let's say the box and triangle are having similar breadth and depth dimension. In the same time, we know that the area of triangle section is half of the box. We shall now plug in both area values in the equation, and then the correction factor is obtained. The similar idea of concept now being applied to the section modulus, where firstly, section modulus for all section categories are determined. Again, the box shape is the basis shape. Then, correction factor, or we shall name it as alpha, can be calculated by using the shown equation. Now, we shall relate the values of set of alpha with B upon D ratio. From the relationship, equations can be extracted, and the equations and those equations are very useful in this method. On your screen now is the overall steps for this simplified method. First, we input the parameters of breadth, depth, and thickness and select our sectional shape, either box, typical, midship section, or triangular section. Then, we determine the correction factor by using the equations. Depends on our sectional shape, either triangular section or typical midship section. Next is to match our correction factor with the calculated section modulus value. And the last one, our section modulus is obtained. Next section is the results and discussion. Current screen shows the results obtained for model A. Percentage difference are calculated to validate the Marais method. Total bending moment percentage difference between both methods succeeded to achieve about 1%, which is below 15%. Moreover, total bending moment of simplified method result value is slightly higher than the conventional method. This result is relevant and acceptable because in actual condition, the hull is said safer as she is having lower value of total bending moment. For model B, total bending moment of simplified method result value is lower than the conventional method. This result may likely to be happen as Marais method is developed based on estimation approach. However, we can see that total bending moment percentage difference succeeded to achieve 4.05%, which is still acceptable. Now, shall we move to the section modulus analysis for model A? Section modulus obtained through simplified method is lower compared to the value obtained by using the conventional method. This is due to the absence of longitudinal stiffness. Percentage difference is satisfied, and most important, it succeeded to achieve below 15%. Now we proceed to model B. Midship section modulus obtained by simplified method is slightly higher than the conventional method value. This is because of model B has smaller scantling area of midship section if compared to the model A, in which model A is the basis shape for the typical midship section category. However, there is no significant percentage difference. Next is the safety factor analysis. We shall start with model A. Bending stress yielded through conventional method is lower. This results safety factor value obtained by the conventional method is higher. This results is optimistic and robust as in actual condition, the model is much stronger. Let's proceed to the model B safety factor analysis. The bending stress yielded through the simplified method is lower than the conventional method. This results safety factor value obtained by simplified method is higher than the conventional method. Even though the result obtained through simplified method was not as expected, the percentage difference is still under 15%, which it is acceptable. In the table shown on the screen is the overall steps in conducting simplified structural strength assessment. Alright, now let's proceed to the relevance of typical midship section category. Is it applicable and acceptable if hull width chines, for instance, model B, being categorized as typical midship section, in which we know that model A with single chine is the basis? The answer is yes. Based on the analysis that has been made, it shows that only 2.04% difference between section modulus for model A and model B. Based on this research, there are few improvements that can be made in order to increase the accuracy for simplified method of midship section modulus. First is to collect more planning hull model to be added into the typical midship section. Thus, from the collection of data for planning hull model, we can perform a linear regression analysis in order to increase the accuracy. Next is to add another one category of midship section that can be extracted from displacement hull model. And the last one is to make an analysis for all midship section having no deck plating, as this method only considers hull with strength deck. In conclusion, the development of simplified method of hull structural strength for small vessel has been carried out successfully. This is because both of the objectives stated have been successfully achieved, as the percentage difference of total bending moment, midship section modulus, and safety factor for both models are below 15%. Thus, simplified method for hull structural strength assessment can be seen as less time-consuming and less tedious, yet it is easy for everyone to perform this simplified method.
Alright, that's all from me. Hopefully my research will be a very useful research in the future. And thank you very much for your time. See you next time.